Hi, Liam. I recently heard that transformers have sparked a real revolution in the world of neural networks. What makes them so special?
Hi, Jessica. Yes, you're right. Transformers have become the foundation of the most advanced AI systems. They're used in ChatGPT, translation tools, image generators, and even in code writing assistants. Their main advantage is their ability to process information efficiently and understand context.
Why weren't transformers used before? What came before them?
Before transformers, recurrent neural networks, RNNs, LSTMS, and GRUS were more common. These networks process text sequentially, one word at a time, which made them slow and limited, especially with longer texts. Transformers, on the other hand, process text in parallel, which is much faster and more efficient.
That sounds interesting. So, how does a transformer work? What's the core idea?
The key idea is the attention mechanism. Instead of processing words one by one, a transformer looks at the whole sentence at once and decides which words are important for understanding each word. This helps capture meaning, especially in complex phrases.
Can you give me an example?
Sure, take the sentence, Masha gave Misha an apple because he was hungry. To understand who he refers to, you need context. The attention mechanism helps the transformer figure out that he refers to Misha, not Masha.
What are the main components of a transformer?
A transformer is made up of a stack of repeating blocks that process input data step by step. Each block includes several key parts. Embeddings convert words into numerical representations. Positional encoding adds information about word order. Self-attention mechanism helps identify which words are important in context. Residual connections and normalization improve stability and ease of learning. Feed-forward layers perform additional computations for each token. Sometimes a transformer has two parts, an encoder and a decoder. For example, in translators, the encoder reads the input text and the decoder creates the translation. But some models use only one part. GPT uses only the decoder, while BERT uses only the encoder.
What are embeddings and why are they needed?
An embedding is a way to represent each word or subword as a vector of numbers. These vectors are trained so that words with similar meanings have similar numerical representations. For example, the words cat and kitty might have different vectors, but they'll be close to each other, because they often appear in similar contexts. This way, the model begins to understand not just the letters, but the meaning. Embeddings are like the model's memory of how words are used in language.
But if the transformer looks at the whole sentence at once, how does it know the order of the words?
Great question. It's true. The transformer processes the entire sentence simultaneously, but by default, it doesn't know which word comes first. To give the model a sense of order, we add positional encoding, special numerical vectors that are added to the embeddings. Each word gets a unique position vector based on its place in the sentence, first token, second, third, and so on. This way, the model can understand that the cat ate the mouse and the mouse ate the cat mean different things.
How does the attention mechanism work?
Attention is probably the most important and fascinating part of the transformer. Imagine that each word in a sentence wants to know which other words are important to it. To do this, each word creates three vectors. Query: what am I looking for? Key: what information do I have? Value: what do I offer? Then, each query is compared to all keys in the sentence. This helps determine which words to focus on. Based on these attention scores, the model uses the values to form a final representation of each word, like focusing on what matters. For example, in the sentence, he took an umbrella because it was raining. Attention helps understand that rain explains why he took the umbrella.
Why do people talk about multi-head attention?
Because one attention head is just one way of analyzing the data. But language has many layers: grammar, emotions, logic, relationships between words, etc. So the transformer uses multiple attention heads at once. Each head analyzes the sentence from a different perspective. For example, one head might notice subject-verb agreement, another identifies questions, and another detects contrast in the sentence. Then all their outputs are combined, and the model forms a rich understanding of the sentence's meaning.
And how does a transformer learn? Does it just repeat all these blocks?
Exactly. All those blocks, self-attention, positional encoding, feed-forward layers, are combined into a module, and models often have many such layers, from 6 to several dozen. Each layer takes a step in thinking, quickly evaluating context, identifying important parts, and refining the representation. The more layers, the deeper and more accurate the analysis. But of course, larger models need more data and computing power to train. Training happens on large text datasets. The model tries to predict the next word or fill in missing words, gradually learning to understand language.
After the transformer processes everything, what happens at the output? What does it produce?
That depends on the specific task. The output isn't just one fixed result. It's more like the final thought, from which the model generates a response. Let's look at some examples.
Sure, what about in a translator?
Great example. If we're using a transformer for translation, the model takes input text in one language, say English, and produces a new sequence of tokens in another language, like French. This happens via the decoder, which generates the translation one word at a time, using the encoder's information and previously generated words. It predicts the next word, and so on until the sentence is complete.
What about text generation, like ChatGPT?
In that case, the transformer also predicts the next token, based on what's already been said. Let's say you input, "Today, the weather is..." The model might predict sunny. Then it uses the updated sequence, "Today, the weather is sunny," to predict the next word. This creates a coherent and meaningful text.
What about other tasks besides text generation?
Absolutely. In classification tasks, for example, the transformer can output a label, whether a review is positive, whether an email is spam, or what topic a text belongs to. To do that, the model usually uses a special token, often CLS, that collects summarized information from the whole text, and the final decision is based on that.
What about images or audio? Can those have outputs too?
Definitely. For example, in models like DALLE, the transformer takes a text description as input and generates an image. The output is a set of vectors that's then converted into a picture. In audio tasks, like music generation or speech synthesis, the output could be sound waves or spectrograms. So the principle is the same. The transformer produces a sequence, and another system converts it into the needed format: text, sound, or image.
So a transformer is like a universal brain that can be trained for different goals?
That's a perfect analogy. Exactly. Its architecture is so flexible that it can adapt to different types of input and tasks. And the output, depending on training and configuration, can be anything. The next word, a generated image, or sentiment analysis.
That's impressive. I feel like I finally understand how versatile this mechanism is.
Yes. And that versatility is exactly why transformers became the foundation of modern AI systems. They're like the Swiss Army knife of neural networks.
Where are transformers used in practice?
Pretty much everywhere. Text translation, chatbots, code generation, image and video processing, speech recognition, even music modeling. GPT-4, for example, can do all of that. Extra components are added as needed.
Why did transformers become so powerful?
Because they process data in parallel, scale easily, and work equally well with text, images, and audio. Plus, the bigger the model, the more accurate its answers.
What does the future hold?
New architectures are already emerging, like flash attention and sparse transformers. Researchers are also working to make neural networks more interpretable, especially in sensitive fields like medicine or law.
Thank you, Liam. This was super helpful. I finally started to understand what transformers are.
Glad to help, Jessica. If you have more questions, I'm always happy to chat about AI.